Chapter 6: Heating System Safety Tests. Home performance contractors belong to an association called the Building Performance Institute, or BPI. It is similar to NORA. It does training, research, and has developed industry standards. Home performance contractors are required by BPI to perform preliminary and post-installation safety inspections of all combustion appliances whenever changes are made to the building envelope or to the heating system. The safety inspection includes a carbon monoxide test, then 3 tests to determine whether the combustion gases are vented properly. The first is a spillage test, the second is a draft test, third is worst-case depressurization of the combustion appliance zone, or CAZ. The CAZ is the room the boiler or furnace or water heater is located in. It's where the combustion air comes from. Contractors must act upon combustion safety test results appropriately. The carbon monoxide test. Carbon monoxide is measured in parts per million, ppm. Most carbon monoxide testers calculate as measured and air-free CO levels. For this testing, they use as measured values. Home performance contractors measure ambient CO levels. Ambient means the air in the room. BPI certification requirements state that ambient CO shall be monitored upon entering the CAZ and during the test period for all appliances. An ambient reading of over 35 parts per million is considered unsafe and requires action. They also measure CO in undiluted flue gases, the gases in the heat exchanger before the draft relief air or the draft regulator air is blended with the combustion gases. The reading for the undiluted flue gases at steady state should not be higher than 100 parts per million. Unvented or vent-free appliances are not recommended by BPI. BPI tells contractors to not test them at all. Remember, if you touch it, you own it. Home performance contractors are instructed to stop the audit as soon as they discover an unvented appliance and tell the customer it is dangerous and should be removed. They will return to finish the audit once the appliance is removed. Carbon monoxide originates from incompletely burned carbon. It is dangerous because it prevents the absorption of oxygen into the bloodstream. Causes of CO formation are fuel-rich mixture, improper venting, or too early cooling of the flame. Places where carbon monoxide comes from are unvented kerosene and gas space heaters, leaking chimneys, furnaces, boilers, wood stoves, pellet stoves, fireplaces, gas stoves, gas dryers, and the other gas-powered equipment, attached garages, which could be full of carbon monoxide from cars and lawnmowers and other appliances, candles, kerosene lanterns, and smoking. Carbon monoxide and oil burners. Oil burners' CO production can increase dramatically with incomplete combustion caused by either insufficient combustion air or too much combustion air. Insufficient air will also create smoke, while too much air does not. Way too much air will create a yellow spot on the smoke test paper from unburned oil. A carbon monoxide problem in the building is caused by improper combustion and a venting failure. That's right, we actually need 2 failures for a carbon monoxide event to occur. First, we have to have a problem with the flame, but then we also have to have a venting failure. The burner could be making high levels of carbon monoxide, but as long as the vent system is working, all the carbon monoxide is being removed from the building along with the rest of the combustion gases. As you can see from the graph on the right side of the slide, when excess air is low, carbon monoxide is high because the flame is starved for air. As excess air increases, carbon monoxide drops dramatically up to a point. Then, at this low point of the curve is where we want to set the combustion air. Once the excess air goes higher than this point, then there is too much air for the flame and CO production starts to rise again. Ambient carbon monoxide. BPI certified contractors are trained that whenever they are running combustion appliances for testing, to monitor the ambient CO levels in the room in which they're working. If at any point the CO level in the room goes above 35 parts per million, they are instructed to turn off the appliance, open the doors and windows to provide fresh air, and then go outside until the carbon monoxide drops to a safe level before returning to the CAS. We should be doing the same thing. When the ambient air goes above 35 parts per million, the home performance contractors are supposed to tell the customer that they should call a heating technician to come and inspect and repair the system. That's when you get involved. Combustion air supply problems. One of the major causes of CO events is insufficient combustion air in the combustion appliance zone. This can be a hard problem to diagnose because when entering the CAS, we open the door and this allows the pressure to equalize, supplying fresh air to the room, temporarily fixing the problem. So we have to look for clues that the burner was starved for air when the problem occurred. Here are some hints that there was an air supply problem at one time. Odors or smoke in the building when the unit runs. Carbon monoxide detector sounds an alarm. Soot or rust on top of a unit, in the burner air tube, and in the throat of the draft regulator. Customer complains about the burner rumbling. There are soot streaks around the inspection ports, and of course a sooted up CAD cell and drawer assembly. Here are some carbon monoxide remedies. First, do not use unvented combustion appliances. Next, inspect and tune up combustion appliances properly. Be sure all venting systems are operating properly. Be sure there are no holes in the furnace heat exchanger or leaks in the returns in the combustion air zone. Install carbon monoxide detectors on each floor and bring in combustion air from outdoors. If there is a combustion monoxide problem in the house, the first test that the home performance contractors are required to do is a spillage or backdraft test. Spillage occurs when proper negative draft is not established in the venting system and the flue gases spill from the appliance into the building. This happens when the atmospheric pressure is greater than the air pressure in the combustion air zone, so the burner is forced to pull its combustion air down its chimney. This is called backdrafting. Spillage also leaves behind visual signs, such as rust and soot on top of the unit and on the floor around the unit. To check for spillage, turn the unit on and use the back of your hand or a smoke stick to see where if heat is coming out of the inspection door and around the burner. Check airflow around the draft diverter or draft regulator to be sure that within 1 minute of firing, the flow is from the building into the venting system. For induced draft heating units, check for spillage at the base of the chimney. Spillage that occurs under normal building operating conditions should be addressed immediately. Spillage should also be checked under simulated worst case conditions, which we'll talk about in a few minutes. The next test home performance contractors perform is a draft test. To do this, take a pressure measurement in the flue pipe with reference to the combustion appliance zone. In other words, hold your draft gauge in the room and stick the probe into the flue pipe. Draft should be measured in a hole in the flue pipe 12 inches from the draft diverter for gas and between the breech and the draft regulator for oil. Remember, never test in an elbow. Okay? Draft should be measured under steady state conditions, that is, after about 5 or 10 minutes of operation. Acceptable draft is dependent upon the outside temperature and the appliance. A minimum of negative 2.5 to 5 pascals is required. That converts to negative 0.01 to negative 0.02 inches of water column. This is what's required for the unit to pass the BPI draft test. Worst case depressurization test is a safety test to see if there are combustion, air, or draft problems. If all the windows are closed and all the exhaust fans are on, will combustion gases still go up the chimney? That's what we're trying to figure out. The test determines how strong the negative pressure in the combustion air zone is with respect to the outdoors and to the rest of the building. Then it determines if the appliance vent will create negative draft under that condition, and if so, how strong is the chimney draft. Fan wars. There are a lot of fans in homes these days. There's fans in the bathroom, there's fans in the kitchen, there's the blower for the furnace, there's the blowers for the air conditioners, there's clothes dryers. When they are all turned on, they create a large pressure difference between inside and outside the home. When the air pressure drops inside relative to the atmospheric pressure outside the house has said to have gone negative. Here are some of the average amounts of air in cubic feet per minute that a fan can draw. A clothes dryer pulls about 200 CFMs. And the problem with this is, of course, the clothes dryer is also usually installed in the combustion air zone right next to the boiler. Kitchen range hood fans can pull 200 to as much as 1,200 cubic feet per minute. Bathroom fans pull somewhere between 25 and 90 CFMs. An open fireplace damper is about, in other words, a fireplace flue pulls about 500 CFMs. Fuel burning appliances with sealed combustion pull about 35 CFMs. The blower on a warm air furnace, again, one of the biggest blowers in the house, 1,200 CFMs. We also have central vacuum systems, attic ventilation fans that can cause depressurization problems. Notice on this list that one of the smallest draws is the amount of draft that the fuel burning appliance can create. So it's not hard for us to be overpowered by all the other fans. Depressurization test steps. Before doing the test, be sure there is no fire or hot ashes in the wood stove or fireplace. The test will take the house negative, so air will be pulled down the chimney. This could rekindle the smoldering ashes and pull the sparks and smoke into the house. Be sure to close the attached garage door. There are probably hazardous chemicals, cleaners, degreasers, insect repellents, and poisons in the garage, as well as carbon monoxide from the cars and other internal combustion engines, and possibly gasoline fumes. You do not want to suck any of these fumes from the garage into the house. Be sure to turn off all the combustion appliances. Close all exterior doors, windows, and fireplace dampers. Now, with everything off, test the pressure in the combustion air zone with reference to outside to establish what we call a baseline pressure. You can do this by sticking the probe from your manometer, your digital draft gauge, out of the building through a cracked open window in the combustion air zone. If there is no windows in there, you may have to buy a long hose for your tester so that you can take it up the stairs and stick it out through the bottom of the upstairs door or window. Once you've established your baseline pressure, then turn on all the exhaust fans, the furnace fan, and then use your manometer to test the air pressure difference again between the combustion air zone and outdoors. Open or close interior doors to create worst-case depressurization, that is, to make the difference the biggest in the combustion air zone. This picture shows the steps for the depressurization test. Once you have created worst case, fire up the water heater, if it is a separate unit, and test it to be sure it's operating properly. Then fire the boiler or furnace and check the draft over fire and in the flue for all the combustion appliances for backdrafting and spillage. Also check for carbon monoxide ambient and in the undiluted flue gases. The results you're looking for are negative 0.2 inches of water column, negative 5 pascals over the fire draft, less than 35 parts per million carbon monoxide ambient, and a 0 to trace smoke. If any appliances fail the spillage or draft test under worst case, repeat the test again under normal conditions. If they still fail, determine the reason and fix the problem. Fixes for depressurization. If the building air leaks are sealed and the fans are stealing all the oil burner's combustion air, the best fix is to bring fresh air from outdoors to the combustion appliance. If you can do this with either a fan in a can, an air boot on the burner, or an air box on the burner. The return air duct should also be checked for leaks in the combustion air zone. If there are leaks, the furnace blower, the largest fan in the house, is pulling air out of the combustion air zone and sending it up into the building. That's right, the blower on the furnace is depressurizing the burner on the furnace. It's committing suicide right there in front of you. The following are the fixes for depressurization of the CAS. First, seal up those leaky ducts, especially leaky returns in the combustion air zone. Bring in point source ventilation for problem devices. In other words, bring air to the burner. We call this isolated combustion. Install carbon monoxide detectors on every floor, and advise the customer to only run one big fan at a time, and don't run fans if there is a fire in the fireplace or wood stove. When you're visiting your customers' homes, you're going to find conditions where it's clearly important that they call in home performance contractors. Some of these are ice dams, the ice that builds up on the eaves of the house, causing the ceilings to leak and water damage in the home. Obvious big air leaks in the house, wet insulation, drafts in the living area, moldy, rotten attic rafters or floor joists, vents that exhaust into the attic, basement, crawl space, or into the walls, knob and tubing wiring, unsealed and uninsulated can lights, and finally, cold rooms. Other things that indicate that there's a problem in the house could be daylight you can see through the sills or basement walls. In other words, if you can see daylight through the walls while you're standing in the basement, those are probably big leaks. Moving cobwebs, blowing back and forth inside of a cellar, indicate leaks. Customer complains about drafts, cold spots, or high heating bills. And finally, any of the air leaks and insulation issues we've talked about today. First thing that the home performance contractor is going to suggest is that the customer allow them to do an energy audit. The energy audit will identify energy consumption for each major energy using device, recommend energy conservation operation and maintenance procedures, estimate the costs of any energy retrofits, project savings for the retrofits, note current safety, health, and comfort issues and how they may be affected by the proposed changes, and explain behaviors that the customer may be doing that waste energy.